In this last section, we're going to take a look at how the higher centers of the brain actually control a lot of those autonomic reflexes, and then we'll consider the effects of aging on our system. So remember that the medulla oblongata is the control center for many of these autonomic functions. And what's going on is that we're going to have this cranial nerve 10 coming in here. Remember, cranial nerve 10 is the wanderer going to most of the viscera. It's going to have a sensory component to it, and that sensory information is going to come up, and it's going to end up getting information to a lot of our higher centers. So if we think about the hypothalamus, you know that the hypothalamus is controlling body temperature, hunger, thirst, and the pituitary gland down below it. And all this information is either going to come out via hormones here, or it's also going to send information back down to the medulla oblongata. We've got the limbic system. And the limbic system, recall, is very tied with our emotions, along with memory. And that's going to influence blushing, because that's an emotional state. Pallor, which is when your face goes white and you have loss of blood, because that's going to be constriction of those blood vessels. Fainting or cold sweating or racing hearts, all of those are autonomic actions. Then we've got the cerebellum, and the cerebellum back here is going to be a lot involved with getting proprioception and comparing that to what we're seeing visually. So that's going to be a lot of our problems with motion sickness and nausea and sweating and different cardiovascular changes. It's going to be influencing those centers in the medulla. And in the cerebral cortex, if you think about, remember your prefrontal cortex here, it's going to be very tied to personality, and the temporal cortex tied in with emotion and part of that limbic system. So they're all going to be influencing our medulla oblongata and a lot of those centers in here. And many of the autonomic centers are beyond the medulla as well. So you can see up here in the midbrain, we've got a urinary bladder control center. In the pons, we have the pneumotaxic and apneustic centers, which influence the respiratory rhythmicity center down in the medulla. We have the cardiac control center down there and the vasomotor control center. So all of those were in the medulla oblongata, and they're getting influenced by these higher centers here. As they are, then the medulla oblongata is going to send out information down the spinal cord, specifically for sympathetic information, but we'll have 7, 9, and 10 coming out from the lower pons and in the medulla oblongata as well. 3, if you'll remember, for the pupillary reflex is coming out from the midbrain. This chart is in your book, and I wanted to point out some of the autonomic reflexes that I do want you to know and some that are less important for you to know. So in the lungs, you've actually got stretch receptors that as you breathe in, take a nice deep breath in, they're going to set a signal off and prevent you from breathing in too much, because if you breathe in too much air, you cause too much pressure, you could actually damage some of those alveoli. In little teeny babies, sometimes this isn't developed fully enough, and they can actually have problems with over inhaling, but that grows in pretty quickly. It's also going to have an effect on heart rate and vasostimulation or vasodilation. Don't worry about those J receptors. We'll deal with them later if we deal with them at all. In the aorta, we've got 2 different types of receptors. We've got chemical or chemoreceptors, and then we've got baroreceptors. The chemoreceptors are responding to gases, so concentrations of carbon dioxide and oxygen. And don't worry about this details now. We're going to hit this plenty when we hit the respiratory chapters. But depending on the concentration levels there, that's going to kick off a reaction to either make you breathe faster and deeper or slower, depending on how those concentrations change. They'll also affect heart rate and vasoconstriction so that we can manage how much blood is flowing through the lungs. Not chemical, but relating straight to pressure, we have got baroreceptors, which you've probably heard about in anatomy. You've got those in the arch of your aorta and up in your carotid sinuses. And those are responding to changes in pressure. If the blood pressure drops too low, it's going to kick off a signal to your brainstem, to your medulla oblongata, to increase the blood pressure. So it does that through the cardiac control center and the vasomotor control center. We've also got stretch receptors in your heart. And when we get to the heart, you'll hear about atrial natriuretic peptide. That it's going to, when we get to the kidney, we'll be talking a lot about that really, and that it's responding to changes in blood pressure in the heart. But as a reflex goes, we've got a hormone called antidiuretic hormone, which you've already heard of. That antidiuretic hormone basically prevents you from peeing so that you retain water more. Well, if you've got too much blood pressure in your heart, this can actually reduce the amount of antidiuretic hormone so that you actually will pee more and can reduce some of the blood volume. So these are all just autonomic reflexes that are going on all the time based on signals that your body is giving to you. We've got stretch receptors in the ventricles. These are the ventricles of your heart. And again, that's going to decrease your heart rate and allow for vasodilation if they are getting too filled up. And then last one is the gastrointestinal tract. So stretch receptors there, that's going to tell you that, oh, you're getting full. That's feelings of satiety. Or if you're getting gas pains, if they're getting bloated, they're going to be stretching out. That's going to cause discomfort, and that's going to cause that reflex to happen. So those are some of the reflexes. I just want you to understand how this is all kind of tied in to that last page, that page of the higher centers controlling these lower centers here. One condition I do want you to know pretty well is this autonomic dysreflexia. This is a pretty severe condition that occurs in people who have had especially spinal cord injuries or brain injuries. You see it a little bit less so in people with heart attacks, myocardial infarction, or pulmonary edema, but it does happen. And basically, what happens is that you're getting an extreme sympathetic response that gets out of control, and that can drive the blood pressure up to dangerous levels. So I'm going to give you an example of what happens in a spinal cord injury. And for a spinal cord injury, for this kind of thing to kick off, it really has to occur at a level of T6 or above, because that way you're going to have that much more of an uncontrolled sympathetic reflex going on. So here's kind of the order, and I want you to be able to put these back in order if I was to ask you a question about it later. So start off with spinal shock when we get the cord cut, and at that point, basically no autonomic reflexes are going on. So everything gets silenced for a while. As things start to heal, then we're going to have this lower part of this cord below. It's not dead, it's just cut off from the brain and the upper nervous system. So there's still blood supply going to the lower cord, and you're going to have sensory information coming into it, and you'll be able to have reflexes going out of it. So you'll actually be able to see muscles going into spasm, even though there's no control from the higher center, because it's all reflexively done. So in this case, what happens is you get an exaggerated sympathetic response. So here we've got a picture of a bladder that's getting overfull. That's going to send a signal off to the spinal cord, and we get this exaggerated sympathetic response. So alpha-1 receptors are getting triggered a lot, and that's going to cause vasoconstriction. So everywhere below, because of our law of mass action here, everywhere below the spinal cord, it's setting off this huge sympathetic response. We're going to get vasoconstriction, which is going to shunt blood away from the skin. It's going to, in doing that, it's also going to raise our blood pressure. So the blood pressure starts going up, all because of vasoconstriction below this cut in the cord. That's going to signal our baroreceptors in the arch of the aorta and up in the carotid sinuses. Those baroreceptors are sensing blood pressure all the time, and as they get stimulated, they get stretched, they're going to be signaling our cranial nerve 9 and 10 that's going to the medulla oblongata. And that's going to be right in the area of those cardiac control centers and the vasomotor control center in the medulla. So they're going to react by increasing parasympathetic system, decreasing sympathetic nervous system. So that way we get a slowing of the heart rate. And if we're increasing the parasympathetic system, we may get some nasal congestion. If we're decreasing the sympathetic nervous system, we're going to be opening up those blood vessels in the skin above where the break was. And that's going to cause the skin to get red and flush and sweaty. But again, only above the spinal cord, because the sympathetic has to come down the spinal cord, and it's going to get stopped right at this break. So everywhere below the break in the spinal cord is still going to stay cool, and it's going to have goosebumps because it's cold. But everywhere above it, it's going to get hot and flush and sweaty. So those two conditions keep going on until you relieve whatever condition it is that's causing you to have that sympathetic response below. So you still could be having high blood pressure even though you've tried to adjust your parasympathetic and sympathetic. And that's why it's so dangerous. So you have to relieve the cause of the stimulus that's causing this to kick off the sympathetic system. And you can treat this with medications as much as you can to get that down as fast as you can. Okay, so let's just wrap up here on aging a little bit. And basically, the main thing about aging is that it's associated with increased levels of sympathetic activity. So if you've got sympathetic activity all the time going on, remember, because all your blood vessels are only innervated by sympathetic system. So there's got to be some amount of sympathetic activity. Your body just loses control of that a little bit and starts increasing that sympathetic activity as you age. And that can put you at risk by itself for hypertension and different types of cardiovascular diseases. And that pretty much wraps everything up for this chapter. I'm just bringing this chart back to you now because now this chart, you should be able to look at it and understand it much more clearly. We've talked about just about all of these organ systems and looked at how the sympathetic and the parasympathetic systems counter each other most of the time. Then we saw a few complementary and cooperative effects there. We saw that the parasympathetic is all done by muscarinic receptors, and the sympathetic is all those alpha and beta, with the exception of a couple places of muscarinic or acetylcholine in the skeletal muscle and down in the glands as well. So you should be able to differentiate the alpha 1s, alpha 2s, beta 1, 2s, and 3s reproducing this graph. And I'll leave you here with the last slide. I thought this was just kind of nice because we've been talking about a lot of these neurotransmitters, and it puts them all together just on one little space, letting you know, reminding you what they do. You don't need to be able to draw them out chemically here, but it lets you see really how similar they are to each other as far as the alphas and the betas and how we deal with dopamine. So these are all our catecholamines up here. We haven't really talked a whole lot about serotonin and endorphins, but we will in the class as we go on. But again, I just thought this was a good place for you to put everything all together. And that wraps up this chapter. I'll see you in class.